Hello. Okay, so now we're going to move on to section 6.2, which deals with applications of the normal distribution. So it turns out the areas under the normal curve can be used to represent probabilities. Remember, what's the maximum area under the curve? 1. The minimum would be 0, so that coincides with our theory for probabilities. So as long as you have a variable that is normally distributed, it takes on a normal shape, or approximately normally distributed, we can use the normal distribution to compute probabilities. One example would be the average scores on any type of assessment. They're typically normally distributed, and the average is around 70%. So in order to use the normal distribution to compute probabilities, somewhere in the problem it has to state that the variable is normally distributed or approximately normally distributed. And when we work out this problem, we're going to have to convert any x value to a z value and then look up the probability in the table to determine the area. So let's look at an example. Let's say that for a Math 165 class, we know that the test scores are normally distributed. The mean is 70. The standard deviation is 5.5. We want to calculate the probability that a student will score more than 85 points on the exam. So step 1, we draw the normal distribution. The mean is at the center at 70. Standard deviation is 5.5. Step 2, we shade the area that we're searching for. Remember, this area now represents a probability. So in this case, we want the area to the right of 85. Now, since we want to look up the area in Table E, we have to convert the x value, 85, to a z value using this formula, x minus mu over sigma. So x is 85, mu is 70, the standard deviation is 5.5. Remember, order of operations, we have to subtract in the numerator first, then divide by 5.5, round to two place values, 2.73. I like to draw a z-axis below the x-axis, just so it kind of mirrors our the x values. So the z-axis, the mean is always 0, and for this problem, 85 corresponds to a z value of 2.73. Now we're just going to turn to our table. We're going to look up 2.73. But remember, when you look up 2.73, that's going to give us the area to the left. We want the area to the right. So if you recall the rules we learned, you're going to look up 2.73, get 0.9968. We want 1 minus 0.9968, and that's going to give us 0.0032, and that's going to represent the area to the right of 85. And so let's just summarize our steps. Step 1, you draw your normal distribution, label mean and standard deviation. Step 2, you shade in the desired area. Step 3, convert x values to z values using this formula here, our z-score formula. Don't forget to round to two places, and then look up the z value using your rules from the previous section to find the area. Let's work out another problem. Let's take a look at, there's a few problems for you to try. We're going to work out number 3. So the average time it takes to read Leo Tolstoy's classic book War and Peace is 60.23 hours with a standard deviation of 13.5 hours. Assume that the time to read this classic is normally distributed. Find the probability that an average reader will finish the book in less than 48 hours. Well, draw and label the normal distribution. So we have our normal distribution here. The mean is 60.23. We want less than 48, so 48 is kind of where the edge of this shaded region is located. We calculate z, 48 minus 60.23 divided by 14.5. That's going to round to negative 0.91. So we can see on the z-axis, 48, which isn't written down here, but it's this edge, coincides with negative 0.91. And all we have to do is to look up this area in our table E, and we're going to get the area to be 0.1814. So the chance that a person will read this classic book, War and Peace, very long book, very intricate, complicated book, is 0.1814. And so go ahead and work on the other two problems using this methodology. And we'll come back and look at what are called cutoff scores next.